Hi and welcome to part 1b of this series of presentations about the alkylation of alcohols. In this video I'll show you some specific examples of the alkylation of alkoxides for the preparation of ethers. I'll start with the alkylation of primary alcohols and continue with secondary alcohols, tertiary alcohols and finally with phenols. In this example, an amino alcohol was selectively alkylated at oxygen. Despite the use of an excess of potassium hydride as base, neither alkylation of the amino group nor extensive elimination occurred. This is an example of biphasic Williamson ether synthesis, again with a tosylate as electrophile. Unfortunately, a huge amount of phase transfer catalyst was used, what may cause problems during the isolation and purification of the product. This here is a rare example of a high-yielding alkylation of an alcohol with a secondary alkyl chloride. Again, a phase transfer catalyst and aqueous sodium hydroxide as base were used. In dipolar aprotic solvents, the nucleophilicity of alcohols can be high enough to enable their alkylation without the use of any additional base. Here, a secondary alkyl bromide could be converted into a methyl ether by treatment with an excess of methanol in NMP at 130 degrees Celsius. The resulting hydrogen bromide probably converted NMP into the hydrobromide salt of 4-methylaminobutyric acid methyl ester. Alpha-halocarboxylic acids can sometimes be converted into ethers with surprisingly weak bases, such as DiPA in this case. The reason for this is the formation of an intermediate alpha-lactone upon deprotonation of the carboxylic acid. Alpha and beta-lactones often act as alkylating reagents and not as acylating reagents. When this reaction was conducted with a stronger base, such as for instance an excess of sodium ethoxide, then elimination occurred to a substantial extent. Because tertiary alcohols are generally difficult to alkylate with electrophiles that can undergo elimination, the inverted strategy of ethylating an alpha-hydroxy ester only gave a low yield of the target product. Secondary alcohols, such as menthol in this example, are generally more difficult to alkylate than primary alcohols. In this case, the alkoxide was prepared from the alcohol and sodium, and the alkylation with chloroacetic acid proceeded in high yield because no elimination could compete with the alkylation. Chloroacetic acid had to be converted into its sodium salt, however, and 2 equivalents of alkoxide were therefore required. A number of different strategies were tested for the preparation of the target tertiary alcohol of this example. The most practical turned out to be the alkylation of the starting secondary alcohol with the epoxide of prenyl bromide, followed by reductive ring fission of the oxyrane. Much lower yields were obtained when the etherification was conducted in DMF or with potassium terzbutoxide as base. Also in this example, a good yield of ether could be attained, but only with a large amount of 15 crown 5 as additive. The electrophile was the ditosylate of diethylene glycol. This type of electrophile does usually not undergo elimination because this would yield enol ethers, and these are not readily formed. Moreover, as mentioned above, sulfonates are not eliminated as readily as halides. As an alternative to the large amount of crown ether, the use of triglyme or diglyme as a solvent may probably also have worked. As shown here, simple primary alkyl halides will often undergo extensive elimination when treated with secondary alkoxides, in particular at high temperature. And with the secondary alkyl halides, elimination may become the main reaction. One trick to circumvent this problem is to use an allylic electrophile and to hydrogenate the product. In this example, the secondary hydroxyl group of an advanced intermediate containing an additional but protected secondary hydroxyl group and a tertiary alcohol had to be ethylated selectively. Unfortunately, silyl ethers can be cleaved by strong bases, and this occurred to some extent under certain conditions. When a lithium amide was used as base, no reaction occurred because lithium alkoxides show only low nucleophilicity. An excess of a sodium amide yielded exclusively the desired ethyl ether, but conversion after 50 minutes was low. A still larger excess of sodium terzbutoxide and ethyl iodide in DMF gave a high conversion in only 5 minutes at 0 degrees Celsius, but partial cleavage of the silyl ether occurred. A similar result was also achieved with diethyl sulfate instead of ethyl iodide as electrophile, again in DMF and at 0 degrees Celsius. Thus, the choice of solvent and electrophile can have an impact on the rate and selectivity of such alkylations. The difference of the nucleophilicity of primary and secondary alcohols is usually not sufficient to enable selective alkylations of primary alcohols in the presence of secondary alcohols, as shown in this example. Only with sterically very demanding electrophiles, such as trityl or diaryl methyl derived electrophiles, such selective etherifications are sometimes possible. In this interesting example, a secondary, rather acidic alcohol was alkylated with an alkyl bromide and potassium hydroxide powder as base in benzene. Saponification of the ester apparently was no issue, probably because of the hydrophobicity of the reactants and the solvent. In this example, a secondary alcohol had to be alkylated with a secondary benzylic electrophile. Under basic conditions, mostly elimination occurred, and only a low yield of the target ether could be attained. The synthesis succeeded, however, when the etherification was conducted under acidic conditions with an acetimidate as electrophile. I'll discuss these imidates more thoroughly in the next presentation of this playlist. The formation of 3-membered rings is a fast reaction, and epoxides can be readily prepared by base-induced cyclization of 2 haloalkanols. In this example, the cyclization was brought about by aqueous potassium hydroxide. Tertiary alcohols are difficult to alkylate, and these reactions usually only succeed with small, highly reactive electrophiles that cannot form alkenes, for instance methyl iodide, alpha haloethers, and benzylic or allylic electrophiles. In this example, a benzylic tosylate was used to alkylate an acidic tertiary alcohol, but the yield was low. The antihistaminic clemastine is difficult to prepare in high yield, in particular if an enantioselective synthesis based on the use of an enantiomerically pure tertiary alcohol is attempted. The reported yields of the etherification shown on this slide only range between 35% and 50%, what is a problem because both reacting partners are advanced, expensive intermediates. In this example, a tertiary benzylic alcohol was butylated with a large excess of butyl iodide in DMF. Again, the yield was low. Intramolecular alkylations of tertiary alcohols can, however, proceed smoothly and give high yields of ethers, even under basic conditions. In this example, a substituted tetrahydrofurane was formed by intramolecular alkylation of a tertiary alcohol with a mesylate as electrophile and sodium cyanide as base. Also in the second example on this slide, a sulfonate was used as electrophile in a polar aprotic solvent, resulting in a high yield of spirocyclic ether. Here, a bis tertiary diol was selectively monoalkylated with 1,4-dibromobutane. After the first alkylation, however, the second bromide underwent complete elimination. This is a rare example of the alkylation of a tertiary alcohol with a tertiary halide. Under optimized conditions, with a tertiary alcohol as solvent and with imidazole as weak base, a low yield of bis-terzbutyl ether was obtained. Propargylic alcohols are slightly more acidic than saturated alkanols, and with 2-methylbutinol the yield of ether was even higher than in the first example. Phenols are more acidic and generally much easier to alkylate under basic conditions than aliphatic alcohols. Most phenols can even be alkylated in water with sodium hydroxide or carbonate as base. This example shows that phenolates are more nucleophilic than anilines, and aminophenols can therefore be selectively alkylated at oxygen. In this example, a 2-nitrobenzene sulfonate was the electrophile, which reacted much faster with a phenolate than a primary alkyl chloride. Under such mildly basic conditions, elimination is only rarely observed. Even with secondary alkyl halides, high yields of alkylated phenols can be attained without using a huge excess of electrophile. In this example, mild potassium carbonate was the base, and a phase transfer catalyst was required to enhance the reaction rate. this example, a phenol was successfully alkylated with only a slight excess of a secondary enantiomerically pure mesylate. Cesium carbonate turned out to be the base of choice. Nitrophenols are still more acidic, and the phenolate anions therefore less nucleophilic and more difficult to alkylate than other phenols. Still, as shown in this example, nitrophenols can be alkylated, even with secondary alkyl halides, but only few examples have been reported. Usually, it is easier to prepare alkoxy-nitrobenzenes from chloronitrobenzenes by aromatic nucleophilic substitution. On this and the next slide there are some more examples, but many more have been reported. These references can also be found in the description of this video. The next presentation is about the etherification of alcohols with some other electrophiles, some of which can even be used under acidic conditions. This can be useful when a standard etherification under basic conditions is not possible because of competing elimination or other side reactions. See you then.